My name is Nikolai Yasutis. You might not know my name very well, but you might know my books. A little bit of them, actually, at least. Oh, let me see. My focus is not where it should be. So I'm an author of a couple of books about templates, standard library, etc. And there are some new books about templates and C++17. And I should point out that I always write because I don't understand C++. And I need a book to explain it to me again and again and again, because I forget everything and everything gets crazy and more crazy and even crazier. And this is what the talk is about. The talk is about the problem an ordinary, stupid, maybe naive application programmer has when they want to write a pretty simple class, just having 2 strings, and make it perfect. Here's the class I want to write with you together. The class is a class customer with 3 members, a first name, a last name, and an ID. And the first name and the last names are strings. So what's the problem here? Well, first of all, we need a constructor. And I will only talk about this constructor the whole hour, nothing else. And the problem with this constructor is at first not obvious. We do it the way we learned it. So we take a const string reference because we don't want to copy the string when it gets passed, because copying a string is pretty expensive. So we take them by reference, and by the way, the second and the third argument have default arguments, so we can pass only 1 string. And we initialize first name, last name, and ID by the passed arguments. So I want to create a customer C initialized with 2 string literals and an integer. And here's my first question to you for the morning to wake up. How many expensive string calls are done here? I mean, how often do I copy or copy assign a string? And which is a malloc unless we have short string optimization. So it's a potential expensive operation. Think about, you have your number? Okay, let's see. In the program somewhere we have the 2 literals, Joe and Fix. The arguments expect a string, so we have to create 2 strings to be able to pass them by reference. So that means we create 2 strings, and that means we have the first mallocs unless we have short string optimization. So assume for the moment these are strings with more than 15 characters. Then you have always a problem. And now we have the first and the second argument, and now we have to initialize first and last, and because we pass it by a constant reference, they are copied again to create our final object, and the initial temporary F and L will get destructed. Okay? You probably know that. Maybe all of you. So we have 4 mallocs. Or 4 potential mallocs. 2 because we create the temporaries, 2 because we copy them to the members of the customer class. So we have C++. We want to make it perfect. Sometimes performance matters. So the question is, how can we make this perfect? How can we improve things? So first of all, what we have done before we went into C++11, we usually overloaded for const character star. So because then we can directly take an address of a string literal as an argument and directly initialize the members by the passed pointers. So we save 2 mallocs. 2 mallocs, only 2 creates we have here. Let's create a string and pass a string and a string literal. Oh, too bad, because now only the first function matches. So we have 3 mallocs, and one of it is not necessary. Because we have the initial problem again. And so, of course, we overload for all 4 functions, for all 4 combinations. And that's what we do if we want to make it perfect in C++, both 3 and 98. Good. Now we have move semantics. So what happens if we move? So we no longer need the string s here. So I want to move it into the created object. How many mallocs? 2. Because there's no move support in the constructor of the string class. So we create a copy when we initialize it. So that means, yes, we pass it to the parameter f, but when taking f to initialize first, we create a copy, and the second copy is for creating the temporary. Which is not good. Well, not perfect, I should say. It's usually fine. So how can we make this perfect? Overload for an R-value reference. So use move semantics in the constructor. OK, let's do that. Let's overload for an L-value reference, a constant L-value reference, for all the places where we don't need move semantics. And let's use an R-value reference for move semantics. And by the way, move semantics covers both moved L values, so moved existing objects with names, and temporary. So a string literal will be covered by that. So we don't need the const character star overload for the moment. So when we have now our initial, our creation of a customer C, and we have our string literal somewhere in the program, we create f and L. We call the second constructor. So we create a string. We still need a string, but this string is a temporary. And the good thing with this temporary, when we have move semantics, is we can steal the value. So what happened here is when we then initialize the string, we steal the heap memory of Joe, and we steal the heap memory of Fix, which means 2 mallocs only, because we still create temporaries, but copying them got cheap. And that's our final object. And we create we delete the temporaries. We destruct the temporaries. So we have 2 mallocs here, 2 to create the temporary, and then we steal the memory, so we move the strings. And move is pretty cheap. It's not perfectly cheap, but it's fine. OK. So, of course, again, we need all the overloads for all combinations. So here are some other examples, so that, for example, if we pass a string and a string literal, we have not 3, but 2 mallocs. And with move semantics, we have now 1 malloc, and that's almost perfect. 10 minutes are gone, and I've explained C++. It's easy. Let's just do it. Oh. Let's pass only 1 argument. It doesn't compile. You know what? You know why? We have too many default values in our constructors. We blindly copied all the defaults. And that means for customer F, we now have 2 matching constructors, which is the second and the last. Oops, I'm one too far. Both match. So if we overload for all these versions and you have default arguments, be sure that you have the default arguments for only one combination and not to make things ambiguous. Okay? So let's remove some default arguments where we don't need them. Let's, for example, choose the default arguments to be used only when we have R-value references. Let's try out something different. Let's use copy initialization. This does not compile, and by the way, it never compiled in any of the versions I showed you, which is surprising. I mean, I create a customer can take a string, and I pass a Nico, and it doesn't work. And this, in general, is a problem. This is a problem we have inherently in the language, because here we have two user-defined conversions. So we first convert the string literal to a string using a user-defined constructor. The library counts as user-defined here. And then we convert the string, the resulting temporary string, to a customer. So this does not compile, what you see here. That's a reason. And that has always been the case in C++. So what can we do with that? Well, it seems we still need our const character star overloads. And of course, all the combinations. Well, strictly speaking, we don't need all the combinations, because this problem with G can only apply to the first argument. Because copy initialization without list initialization, so without curly braces, is only possible with one argument. But not to make it too complicated, let's overload all 9 combinations. You like C++, don't you? And beware that you make the default arguments right to avoid ambiguities. 2 mallocs here. The good thing is we now make it a little bit better, because we don't have moves anymore involved when we pass 2 string literals, because we have the constructors taking the pointers directly. So we have 2 mallocs here, 2 mallocs here, 1 malloc here, and that is, by the way, that is perfect. It can't become better, because we create 3 strings, we pass 5 string literals, so we need 5 creates, and we pass 1 string which we move. It can't become better. We should at least talk about passing by value. Because all this trouble is driven by the fact that we pass by reference. And how many of the problems here can be avoided by taking the arguments by value? Ooh, by value, a string. Let's see. Well, first of all, we still have the problem with the 2 user-defined conversions. So let's make it correct. Let's add this additional single constructor taking a const character star. Now let's count and see what happens. First constructor has 4 mallocs. That's not good, but it works. Because we create the strings, and because we have by value, we don't have references, we pass them to get copied to first and last, to the members. We have the same problem here and the same problem here. So these are 11 mallocs. That's a lot worse than the optimal perfect version of 5, having 5 for these 3 calls. So what is a fix? What is a fix? Move. Yes, move the temporaries into the members. So because you create them when you pass them, so move them to the member, because we don't need that anymore. And now what does that mean? 2 mallocs here because we create 2 strings by we create a new value string here, and then we move this temporary f and l, or this argument I should say, f and l, to the members first and last. 2 mallocs here. One because we copy the string, yes, and that's good. We still need the string. We didn't move the string into the object, and one to create the temporary string for the second argument. And then here we have 1 malloc because we moved the string into the member of first. And cool. Done. So remember where we came from. We started with the problem of having just a string constructor, a single string constructor, taking objects by reference. And it ended up to have something like between 7 and 9 overloads to make it perfect. And with this, we have 2 versions, and we are almost perfect. The additional overhead here is the moves. Well, at least one, which we have because we pass S with move semantics. But, of course, we have something else in the standard, which is called perfect forwarding. So we have an alternative approach, which is, let's pass the elements as a universal reference, or as it is called now in the standard, a forwarding reference, which is an R-value reference of a template parameter, and use forward. Not that easy to implement, but we learned it that way. This covers all 9 combinations and even more. Good. Now, when we create a customer C and pass 2 string literals, then F and L, our arguments, become universal references or forwarding references to these literals. So we don't copy anything. We just introduce new names for them. And the key thing with forward is it does the right thing. Well, it almost always does the right thing, I should say. So in this case, when we have a temporary no, in this case, when we have an L value in a string literal in original is an L value, it takes this to initialize the 2 members first and last. Two mallocs. That's it. Perfect. That's why we call it perfect forwarding. Let's pass a string we have already. 2 mallocs. Perfect. 1 copy of S, 1 create for the fix. By the way, in this version, the type S1 is std string, and the type S2 is const character star. Am I right? No. Why don't you scream? Hey, you're tired still? We pass by reference. By reference means if you pass template arguments by reference, they don't decay, though they keep their original type. Which means that the type of S2 is an array of 4 const characters. But it works. That's a good thing. And we can move, and we have what we had. We have one malloc because we move the string into first, and we create one for the temporary. Done. Thank you very much for your attention. Oh. Why don't I get any applause? Because you knew all of that. That's a problem, huh? Nothing new. What the hell is this guy telling you? Well, I want to motivate the problem. Let's create a single customer just passing one argument. Does this compile? No. What a surprise if the title is but. The error is conversion from const character 5, array of 5 const characters, to a non-scalar type customer is requested. Yes, yes. So what's the problem? The good thing is we have different compilers. One compiler gives me that, another compiler gives me that, and that's a little bit helpful, or more helpful. No viable conversion from const character 5 to cast. Among the different candidates it lists, I think it's Clang here. One candidate template has the following problem. I couldn't infer the template argument as 2. Because template arguments with default values, well, template arguments for, template parameters for call arguments with default values are not deduced. You all know that rule, don't you? So, what is the solution? Well, we have to also place a default for the template parameter. And what is the default here? Const character star. Well, we could also say an array of 1 const character, but that seems to be a little bit strange. So let's do it that way, and let's compile. Let's compile it with GCC. Fine. Let's compile it with Clang. Fine. Let's compile it with Visual Studio. Actually, I don't know which compiler is right. We wrote a new template book of 850 pages, and I don't know which compiler is right. I have to confess. Who knows which one is right? Anybody here? I prepared a few of the slides over the last 2 days. I found it yesterday. I just said, oh, let's make a last try. And by the way, why do I always say the default argument for S2 is std string? Let's use const character star. And suddenly it didn't compile on one compiler. OK. So the good thing is it works if you use std string on all compilers. You like C++, don't you? OK, all problems are gone, but let's extend the test suite because we found that we should try out everything for this simple class. So the next test we do is, let's call a copy constructor. A couple of you know what happens now. It doesn't compile. We have no matching constructor for the initialization of an std string. Note, in instantiation of that function template specialization, customer taking a customer for the customer instantiated as a customer reference, okay, and an std string is requested here. Okay. A const customer copied to another customer compiles. And probably most of you have seen this problem also sometime before. The problem is here. The problem is that we pass a customer and not a const customer. And the compiler now finds two matching functions. One is a predefined copy constructor. The predefined copy constructor takes a const customer reference. We don't pass a const customer, we pass a customer here. Wait a moment. And so our templified constructor is a better match by language rules. So it will be used. And as it will be used, it is instantiated for the first time to be a customer, by the way, to be a customer reference. We come to that in a moment. And as a second type, because we don't pass a second argument, with std string. So this is used to be compiled. And the problem is that the moment, so f is a customer here, and we try to initialize the member first by the customer f. There was a question. No, the question is, why is there a predefined copy constructors? Copy constructors are almost always there, unless you delete them. Before C++11, they were always there. So it's different from the default constructor, which is only there if there's no other constructor. But the copy constructors are almost always there. The only exception is if you have explicitly defined move constructors or move assignment operators. So this is a significant problem. We run into it all the time, even in our standard library. And we have to deal with it. Unfortunately, we didn't fix the language here. We should have done that when we standardized C++11, but now it's probably too late. So we should say, here, the inbuilt copy constructor is a better match. But it isn't. And therefore, we have a problem here. And the usual way to solve this is to use spinne, or enable if. Enable if is the idea to say, I want to ignore this constructor if the following is the case. And I want to ignore this template constructor if I pass a customer. Because, as a first argument, because then I mean a copy constructor, and I want to have this copy constructor called and not my function, which is only there to initialize my members by strings. So the way we can program that, since even before C++11 is with something like enabled if, but in C++11 we have standardized the feature, so we can use a standard enable if with some tricky template techniques here involved, which roughly means behind the scenes, enable if checks whether the check is S1 the same as the type customer, is true or false, at compile time, and if this is false, the whole template is gone, is away, it's not there. So if we pass a customer as in a copy constructor, this is not used. Well, in theory, if we make everything right, we don't have done that already. Yeah. We call that, by the way, spinne it out. So Google became a verb. Spinne became also a verb. And I'm wondering when it is in the Webster or in any other dictionary. It's our fault. In the first edition of C++ templates, we introduced that term. I apologize. Marshall told us that's almost the worst acronym we have in C++. There's only one worse, which is RAII. Okay. So, okay, this is ugly syntax, isn't it? It is. But we have other versions than C++11. So, for example, one ugliness is because enable if yields a type, the type is void and is ignored. The whole trick is to say, we have here a check, but there's no reason we introduce a third template argument. The third template argument is only there to introduce this check, and it yields a type. And because it yields a type, we need type name before std enable if. So in C++14, we introduced something like enable if underscore t, so that we can skip both one leading type name in front of std enable if and the trailing : type. And by the way, that was so cool that I think it was Walter Brown, thank you Walter, proposed to say, well, we want to have it also for traits where we have : value. And so in C++17, we now can write it at least on one line, provided the name of the type trait is not too long. We have some of them. Okay. We still have the error. Why that? Because you see it here. You see that this template is instantiated not for a customer. Well, we pass a customer. It's instantiated for a reference. This is a template instantiated for a reference. Why that? It's a fault of perfect forwarding. Because when we perfect forward, forwarding is a fault. The problem is, if we have move semantics and we pass something with move semantics, so we declare something as an R-value reference, when we use it, it's an L value. And the reason is that move semantics should not be automatically be forwarded. Because if that would be the case, and we use our argument twice, the first use, we would use the value with the first use. So we have a special, very interesting rules in the standard saying that there are some special cases involved to more or less make forward do the right thing. So sometimes calling move and sometimes not. And we need an ampersand here because when we pass this customer object f, the template argument s1 is deduced as an L value. And here's a rule, by the way. It's pretty obvious. It says everything, so why don't you only read the standard and you understood C++? If the parameter type, which is f here, is an R-value reference, which is the case, we have 2 ampersand, to an CV unqualified template parameter, we have a template parameter S1, and it's neither qualified with const nor with volatile. And the argument is an L value. Yes, we pass an argument as an L value. F is an L value. The type L value reference to T is used in place of T for type deduction. And again, this is to make move semantics work fine in generic, more or less in generic code, that we don't need overloads or that we can perfect forward things. Done. We have solved our problem. Thank you very much for your attention. You got it, yeah. Let's see whether the applause raises more. Ring. Hello. Oh. Hi. Oh, you used my customer class? Awesome. Or what? How you derive it? Well, it's clear. You have VIP customers, VIP customers. Oh, I forgot that. You have VIP customers? Okay. Publicly derived from customer. I tell you what, you will get the problem I just fixed. So please have a using declaration so that we inherit all the abilities of this constructor. So that we again can pass 1 or 2 strings and optionally an int. Does everything still work? Does everything still work? If you know the answer, there's no reason to buy our new C++ templates book. Otherwise, there is. Okay. Shameless advertisement. Yes, everything works. I can initialize even a VIP with the equal sign. I can use a copy constructor. So this were the tricky cases here. And everything else also works fine. So great, we're done. What? What do you say? You have a problem? Why? Oh, you tried to create a customer and pass the VIP? Oh, that doesn't compile. Too bad. So what is the problem here? We disable this templified customer in the base class only if we pass a customer reference. But what we pass here is a VIP reference. This is perfectly legal. A VIP is a customer because it's publicly derived. But this does not compile. The strange error we got is you are not allowed to initialize first, the string first, with the VIP. Okay. So we can't use is same. We should use a different type trait. There are a couple of interesting options here. For example, it's an interesting discussion. Should we use is convertible or is constructible here? And just to confuse the Russians, the order is different depending on which one of them you use. Just to confuse the North Korean, I should say, these days. You still get an error? Oh yeah, well, I skipped the ampersand, but anyway, it's okay because the ampersand is no longer necessary because it converts. A referent converts to a non-reference. So what is the problem here? Think about it. Which language rules is broken here? Without saying the answer, who knows what the problem here is? Please raise your hand. 1, 2, 3, 4. Good, cool guys. I sent a bug report to Jonathan because when I tried this out, I got the error message, and the error message was this. So now you understand what's going wrong, huh? So now you got it? The problem is similar to a problem when you get a core dump and you're lucky because you had undefined behavior, and if you didn't got the core dump, even worse things could have happened. And the problem is simple. It's a logical error what we do here. We define a constructor. And while we define a constructor, we say we want to have it if an argument is convertible to a type cast, which needs a constructor. So by defining the rules for how can I create a customer, I asked myself whether I'm available or not. So we were lucky to get this error. By the way, when I tried this out, there's a longer story behind it. In some versions, it did work fine, and then I switched to a slightly different way of enable if here, and suddenly the compiler crashed, which can also be a result of this. Yeah, we made something wrong here. We can't use is convertible to cast. We have to formulate it the other way around. We have to say can't say is not convertible to cast. So we have to say is convertible to string. So we have to formulate it positively because string is not what we define here, and we can use a type trait for strings here. Done. Oh, perfect. Thank you very much. If you don't like the way you have to disable this template, there's light on the horizon, which is called C++20. Because in C++20, we will have a language feature as a side effect of concepts, which is called requires, so that we can formulate this requirement not as a strange enable if type trait library feature. We have now a language feature disabling templates for some cases. So we simply write, this requires that the type S1 is convertible to a string. Otherwise, this template will be ignored. So we are looking forward to C++20. And I hate it. When we wrote C++ templates, the new edition, I don't know how often I thought, I hate to write enable if here. It was a big mistake, really big mistake, that with concepts we played the all or nothing game, which is a serious problem we have in the standard committee right now. People want to have concept all or nothing. And we should have standardized requires, at least requires, because it's obvious that we need it, because we have enable if all over the place. If you look into standard libraries implemented, there's a huge number of enable if statements to fix the problems you just saw and a couple of other problems. Let's summarize. Yeah, there's no further trap. There's no further trap I know yet. Let's think about these three statements. Let's think about C, D, and E initialized by two string literals, by a string and a string literal, and by a moved string and a string literal. And everything else should still work fine. So we started with, we want to have perfect performance for this little customer class. And when we try to reach this perfect performance, we run into trouble. And we try to solve this trouble. So the initial version, as a side effect, after some versions we tried, we came back to the question, why don't we pass strings by value here? And it turned out that this is pretty expensive. 11 potential mallocs, unless we have short string optimizations, because we have 4 creates, and the expensivest thing is that we got with these three statements as a summary, we got 7 copies, expensive string copies, and 1 move. So the solution was here to use std_move for the initialize, for the by value pass argument f and l, and we were almost perfect. We got 5 mallocs because 4 creates and one copy, which is exactly what we had. We had 2 creates for the first statement because we have 2 string literals, then 1 string literal at the second statement, and 1 string literal at the third statement. So that's, we can't avoid that. And 1 copy because the second constructor takes s by value, and it should be its own copy. And then we have, but the overhead to a perfect solution is 5 moves. That's pretty good. The next alternative were 5 mallocs. So that was the perfect solution, but we needed all the overloads. At least 7. 7 or 9. And then we got our easy solution having only 1 declaration. And this was, is also perfect, but it has a strange enable if syntax. And by the way, take your picture now, because now the slide is complete. The first 2 versions still have the const character star problem. So when we use copy initialization with the equal sign and pass a string literal, then, so therefore, in the first 2 versions, to make this available, to enable this, you need 1 other constructor. And the other constructor should just take 1 const character star, and that's all. That's all I want to say. Who's the winner? Who thinks, well, we don't vote for the first version, of course. Who thinks the second version, pass by value, is the best solution here? Okay? Who thinks the third version is the best solution here? Who thinks the last version is the best solution here? And all the others hate C++ or what? Well, is there an alternative I missed? String view? Oh, how many minutes do we have? String view. Okay, I forgot that, to be honest. But string view is not better. It's an alternative, but it's not better. With string view, let me think. With string view, we have, we create, if we pass an std string, we can use it as a string view, that's fine. And if we use a string view to init, so the problem is, if you pass an std string to a string view, and then use the string view argument to initialize your string, you call the constructor. So you still need some overloads for that. So yeah, next time I will discuss that. Okay, any other alternative? What about aggregate initialization? If I make all fields public, are you serious with this question? So then you directly can pass the elements. There's no argument involved in the constructor, so it's better, yeah. So the rule is make all the fields public. Thank you very much. Next time I have a slide for that. Well, any other great contribution, what else we could do? Sorry for that. What? You can use string literals internally in the class? No. In the initialization? String literal? What do you mean by string literals? Yeah, so he's saying when I overload for const character stand, I avoid some overloads. Yeah, but that we had that already. Yeah, okay. The question is, can we in the second case rely on an optimizer to have the same performance as a third, or what? So to help with the moves? Well, in practice, this is not done. I'm not sure. I'm only an application programmer. So anyway, summary. We can afterwards discuss a lot, and you can send me emails. I'm fine with that. And I know I'm not perfect. I only present my view as an application programmer. And you learned again and again, C++ is tricky. You can do everything, and you can make even every mistake. The next thing is, oh, there's missing. My animations are wrong here. Second topic was added late because it turned out that finally I decided that the second option, the second bullet, is a winner. So that we say, let's see. No, it doesn't work. No, we come to that. So, yeah, here it is. So that we pass by value is incredibly good. It's not perfect, but I would recommend this in this case because we have to teach C++ to people. The usage of enable if is a nightmare for application programmers. And by the way, you might think that requires makes it a little bit better. We are currently discussing a couple of trouble we probably get when we have the requires clause in the standard library. Because the requires clause changes the signature of a function. And the moment you have a required clause standardized, and you want to change your requirements, you break binary compatibility, which will be a serious issue. We currently discuss where to apply concepts and how to apply concepts in the library. We have no solution for that yet. Yeah? Yeah, the argument was that the problem of the expensive copying is not there if we have short strings and our implementation uses a short string optimization, which is in most compilers now the case, usually up to 15 characters. So if in your programming language or in your application, your customer names are less than 15 characters, that's fine, that's perfect, or almost perfect. Yeah, there are applications. There are applications of this problem, having a customer with a string member, which is a pretty common thing, I think, where strings are longer than 50 characters. And by the way, yeah, no, yeah, sorry. If we wouldn't have default arguments, yeah, we would not need it. Yeah, you're right. Yeah, but sometimes we have default arguments, or sometimes we have a constructor taking only one string. So it happens. Yeah. So the workaround is you are not allowed only to pass the first thing. Yes. That our APIs derived from the constraints the language give us. Good advice. We have C++ 70 support now. It's good. So some of the features I discussed here are there in C++17, especially the improvements of the type traits. We had a lot of issues. Oh, there's another question. Pardon? Pardon? Well, Clang 4 starts to support C++17, but the major support is in Clang 5. You're right. That's 6. Yeah, so it's plus. It's 4 plus. It's 7 plus. We also have GCC 8. Yeah. Thank you. Templates are tricky. You saw a couple of problems here, which we describe now in the book. And I have to say, I'm not the expert. The experts are the 2 other authors. I only try to understand what they write. That was my task in this book. And just as a hint, I'm also currently writing a complete book guide about C++17. If you're interested, go there. It will be published in a different model than the other books. It will be published as soon as a third of the book is done as an ebook. And you can buy it for very low money and then get for free the updates. Because otherwise, I need 1 more year to make this all done. I have a huge list of issues I learned already this week when I listened to the other talks. So if you're interested, look at that. And I'm still looking for reviewers of that book. The first version will come out in probably 4 weeks or so. And I'm looking forward to C++20. For requires and some other things. That's it. I'm here. I'm still here the whole week. So tomorrow I will tell you my other interesting findings about what I learned about templates when we wrote this 2nd edition. Trainer pedal book signing will be there, and on Saturday, I talk a whole day about move semantics. There's more to tell. That's it. Thank you very much. Please talk to me later. Thank you.